Hello, everyone. Good afternoon. I'm Lauren. All right, I'm going to angle this and stay in my green box. Okay. So like Eden just said, I'm going to be presenting about enabling security defenders with AI. So here's a quick overview of the talk. I'll get into it since it's only 20 minutes long. So first, I just wanted to kind of give you a brief overview of how we're thinking about AI security at Meta. So here, I'm just kind of spelling out like the different areas in which like security comes into play or is a consideration when we're thinking about AI. So there's security of the actual services and systems and platforms and infrastructure that are used for model training and inference. There's also security considerations about the artifacts, meaning like the actual model weights, the training data, the training recipes that are used in developing these models. After that, we need to think about the security implications of the models and the systems that are built on top of the models themselves. And then finally, we might think about specific products that are being launched by the company and the security implications of risks associated with them. So the team that I work on Meta, fits squarely into kind of this third bucket where we're thinking about what are the system and model level cybersecurity risks that are introduced by generative AI. And so going into deep diving into a bit more of how we're thinking about evaluating and understanding these risks. Here I'm kind of separating it out into two big categories of risk that are introduced by generative AI when we're thinking about cybersecurity. So on the left-hand side here, I'm just thinking about a use case where you have maybe a benign developer who's developed an application on top of an LLM. Maybe it's a chat bot, maybe like some kind of like desktop productivity agent. And when we think about the cybersecurity risks that exist in that kind of environment, there's a few bullets here that list kind of like high-level types of risks that we might be concerned about. So one might just be, does the model do things that are risky from a cybersecurity perspective? Like maybe a developer builds an application that has access to sensitive data, and a user can just ask the model, hey, could you just give me the list of like all the contacts of the last person, that was using your system? And the model says, sure, I'd be happy to help you with that. And then one step beyond that, the next bullet gets to the susceptibility of the model, not just to benign or like straightforward requests to do something that is risky, but jailbreaks or some kind of explicit attempt to override model safety. And then building on that, one step further, we might be worried about the case where maybe the user of the application isn't the malicious one. Maybe there's a benign user, but there's a malicious third party trying to achieve some of these same malicious goals by perhaps leaving prompt injection payloads and third-party data that's going to be ingested by the application. And then the fourth bullet there is a case where we don't even have a malicious party at all. We might just be worried about the risks of the model doing risky things or generating cybersecurity risk just due to its propensity to do things like generate code that has insecure coding practices within it. So for everything on the left-hand side here, when we think about how to mitigate these types of risks, it really boils down to kind of a strategy of either trying to modify the base model itself to do a better job of dealing with those, or applying some guardrails on top of the model at the application layer. So in terms of model level safety, we might think of like fine tuning the model to refuse things that it's not supposed to talk about, or it's not supposed to release sensitive information. At the application level, you might think about guardrails like some of my colleagues presented about this morning for Meta, things like Llama Firewall, Prompt Guard. These are like classifiers at the application level that you can put in between the layers between the LLM and the application. To try and flag and eventually enforce against malicious use. Okay, so that's the left-hand side. On the right-hand side, there's a whole different realm of risks that are introduced by generative AI, where instead of thinking as the AI system as sort of the target attack surface that we're worried about, now we're thinking of AI as a tool that the adversaries themselves might be using. And so when we think about the risks from that perspective, what we care about now is not so much, what are the ways in which one can attack the model, but what are the inherent capabilities of the model? If you give this to an adversary, what is the worst thing they can do with it? So in this category, sort of in the top right, when we're thinking about how these models can be used by adversaries, some of the dimensions we're thinking about are how it can be used for social engineering, how models or applications can be developed to automate things like discovering code or network vulnerabilities and exploiting them. And in this case, when we think about mitigating these risks, I would say the strategy is entirely different than the strategy on the left-hand side. Because here, all of these things listed at the top, these capabilities, the solution here isn't basically to try and fine-tune the model to maybe not be good at detecting vulnerabilities, because detecting vulnerabilities and writing exploits is very highly correlated, for one thing, with stuff that we want the model to be good at, like coding, and we're not gonna sacrifice models' coding abilities. Second, a lot of these capabilities are arguably dual use. So thinking about, again, like discovering 0 days in a code base. Of course, it does introduce a huge amount of risk to think about a case where models get so good at discovering previously unknown vulnerabilities in code bases that attackers can just fully automate this process. At the same time, it means that defenders can also automate that process. And if we develop tools on top of that for defenders to apply constantly to their code bases and to their systems, then we can think about uplift not just to the adversaries, but to the defenders as well. So that's why on the bottom right-hand side here, the defense strategy for this bucket of risk, I would say, is just categorically different than that on the left. We're not trying to limit the capability, or we're not trying to like patch anything in particular. Basically, we're trying to see how can the same capabilities that uplift adversaries also be provided to defenders and basically uplift the defenders, ideally more than adversaries are uplifted. Okay, and so in thinking about how to measure all, both on the left and the right-hand side of that diagram, these different types of cybersecurity risks, we often turn to benchmarks as our way to understand kind of how much risk is present in various categories in each of those two buckets. So at Meta, a subset of the evaluations that we use, we've actually open sourced in this repo called CybersecEval. So on the left-hand side, there's just like a screenshot of the GitHub repo there. And so you can see there's kind of like a few different categories actually you can't see, I should have taken a better screenshot. Inside the benchmarks folder, there's a subset of categories of different kind of risks that we measure with these benchmarks. And so this is a set of benchmarks that was put out, I think now, maybe like a couple of years ago was when the first one came out, and we periodically update and add more benchmarks to it. The purpose of making this public is specifically so that developers and researchers can all have access to these same benchmarks, do apples to apples comparisons, and also identify, build on top of existing solutions or like models to build end-to-end systems that they're evaluating against these benchmarks. So in the screenshot on the right, I just have, I see a reference to, I think there was a survey from the AI Alliance about repositories or packages that people use to measure safety and security risks. So CybersecEval was rated highly there. So it has some wider use. On the top left, you see the middle left, sorry, top middle, UKAC has this open source evaluation framework called Inspect AI, which is gaining more and more popularity. It's a really great package. Some of our benchmarks have been integrated into there. And then in the bottom middle, I'm just calling out this. I think this is kind of a cool example. I think at first it was kind of maybe an embarrassing example. I'm not sure. I wasn't on the team at this time. Some people in this room were. They can tell me one of the benchmarks in CyberSecEval that I think was in CyberSecEval 2 is basically some toy challenges for a model to try and, it's attempting to test the exploitation capabilities of an LLM. And so there's basically some kind of like toy challenges where you have like, here's a function with like a specific buffer overflow vulnerability. Can you find the payload that triggers this vulnerability? Something like that. And in the initial publication that we put out with CyberSecEval 2, I don't remember the exact number, but the models were not very capable at solving this challenge. And the way we were giving the models the challenge was literally just, chatbot, copy paste the text of the challenge, like here's the vulnerable function, give me the payload to exploit it, give it to the model. And they don't do very well. But after not very long, because these benchmarks were public, other people started trying to use them, and Google was one of the first ones that built out not even a very complex, but like a simple agentic system that completely maxes out some of these benchmarks. So instead of just giving the challenge to like a chatbot LLM, they provided, so you can't really see the diagram here because, sorry, it's kind of tiny, but this is sort of an architecture diagram of their agent where it has the ability to, have some kind of React loop, and it has access to some tools like a debugger, and it's able to max out some of these challenges. So this was like a really important, I think, example of how making these benchmarks open source encourages developers and researchers to iterate on building systems that ideally max out these benchmarks so we can move on and find the next difficult challenge for models to take on. Okay, so with that brief intro to to CybersecEval, I want to introduce just at a high level a couple of recent benchmarks that we added in the most recent iteration of CybersecEval, which is CybersecEval 4. And specifically, these benchmarks measure defensive capabilities of AI systems. So these would fall kind of like in the bottom right corner of that 2x2 grid that I had up earlier. Okay, so the first one of these that we released, I think, around the end of April is called Auto Patch Bench. And so this is a benchmark that's intended to evaluate the capabilities of an AI system to automatically patch security vulnerabilities in code. And so to give you a concrete example of what this benchmark looks like, it's basically a bunch of specific examples of real-world code bases that have vulnerabilities that were detected by OSS fuzz, so Google's fuzzing that's just constantly scanning all these open source repositories. And so what we give to the model looks something like what you see on the right-hand side here. We're prompting it to tell it that it's an experienced security engineer at Meta, and that it needs to address the following security critical fuzzing crash. And so we're giving it the stack trace that is dumped out by the fuzzer. And then we're asking it to implement a patch that resolves the underlying vulnerability and also maintains the intended functionality of the code. And so I'll get more into this when I talk about the challenges, but it's actually not straightforward to, in an automated way, verify the correctness of the patch that the model spits out. So here's the way that we approached it, was to ask these kind of like incremental questions. First, does the patch that the LLM submits actually build? And if it does, if we resubmit the initial proof of concept that caused the crash to begin with, do we still see that? Okay, if not, then it passes that test. And then also, if we do sort of a more thorough fuzzing, where we don't just give it the original proof of concept, but we start submitting iterations of different inputs, do we see a crash? If not, it's considered to pass that. And I think that one of the key things that makes this really interesting is that if you just stop there and you say like, okay, it no longer triggers a crash, it still wouldn't be a very good evaluation logic, because then the LLM could just sort of cheat by writing a patch that erases the entire code base, right? And it doesn't trigger the crash, but it does not preserve the functionality of the code. So this last kind of criteria here is really the hardest, or like the most important, but also the most difficult to kind of like come up with rules to judge, basically. So here's, let's see, this is, on the left-hand side, this is just kind of another architecture diagram, in this case of a reference implementation that we released along with the benchmark of what an agent might look like that takes on this challenge. So here you have the LLM, you're asking it to generate a patch, you're saying, it basically looks like the example I had on the previous slide. Here's the stack trace. Identify the underlying cause of this security vulnerability and create a patch. And so this is kind of like a simple React loop where the agent submits a patch, and then it has access to like a compile tool, and so it compiles it. And if there's build errors, then it says like, then we basically reprompt it and say like, oh, try again, it didn't build, here's the errors. And then if it makes it through that, Then it again tries the initial proof of concept input that caused the crash initially. If it fails that, again, there's some prompt baked into this like agentic loop. And eventually it submits its final patch. And then on the right-hand side, this just gives you an idea of kind of how some models, when put into this simple React loop, perform on this benchmark. And the takeaway here is not, it's not anything about how the models perform compared to each other, because I actually can't remember off the top of my head, but I think this is actually like a fairly small sample size of different challenges that were given. So there's no statistically significant like conclusions to be drawn about how the models perform relative to each other. But what you can notice is that in general, you see the importance of having these multiple criteria in the evaluation logic, because for most of the models tested, we do see a majority of them able to produce a patch that actually builds. So if that's your only criteria, you would get like an overly optimistic sense of how well models are doing at auto patching. So the yellow bar is the percent that build patches that build. The red bar, I think, is what share of their final submitted patches actually pass like 10 minutes of fuzzing against a bunch of different inputs. And then the last one is how many of them pass all 4 of those criteria that I mentioned before. Okay, and apart from that specific benchmark, there's another category of benchmarks that we've been working on that we'll be releasing soon that are part of what the title here says CyberSecEval, which is not a typo. It's part of CybersecEval, but it's meant to be sort of like a punny name, indicating that these benchmarks are trying to measure how helpful LLMs or AI systems can be to a security analyst within a security operations center, or SOC. So these are benchmarks that we developed and are finishing developing right now with CrowdStrike. And they cover these 3 categories here. So there's one basically testing the models or the system's capability to reason about security incidents. So like we give it some information about the business, the network topology, and then here's a security incident. And then we ask it a multiple choice question about how it would respond or how it would triage. The second one is focused on the model's capability to recognize complex malicious activity in like host-based logs. Here, we're basically giving the system some outputs from malware detonations within a sandbox, and again, asking it some questions to reason about this. And the third one is focused on threat intelligence reports, where we're giving the model in its context window, in this case, image-based, so PDFs of threat intelligence reports, and again, asking it to reason, so asking it some questions that require it to reason about what it's learned from the threat intelligence reports. Okay, I think this is my last slide or my last substantive slide, where I listed out some non-comprehensive list of challenges and learnings in benchmark creation. So one thing that's come up repeatedly is quality control for both third-party and synthetically generated data. So the auto patch benchmark I mentioned is based off of another open source repository called Arvo, Arvo is basically a repository of open source repos along with vulnerabilities detected by OSS fuzz and the corresponding patch that fixed the vulnerability. And so we started working with this because it seemed perfect for our use case, and it was, and it's great, and I don't want to disparage Arvo, but it turns out that like a lot of things that you think are taken as given, you have to go back and check. So in this case, for example, the patch that fixes the vulnerability, they had a heuristic for identifying that, which turns out not to always point you to the actual patch that fixed the vulnerability. So there's a lot of extra work that needed to be done to identify the truly correct patch, so that we could understand if our evaluation logic worked correctly on the actual ground truth correct patches. And similarly for synthetically generated data, for that last set of benchmarks I mentioned, where we're generating these scenarios and asking the model to reason about security incidents, we're often making use of LLMs to synthetically generate a lot of the data. And as I'm sure many of you here already know, LLMs aren't 100% reliable. They can hallucinate at times. And so you need to have robust methodologies for kind of doing quality control on synthetically generated data. I touched briefly on defining verification logic for task success. The ideal is having tasks that you can programmatically verify. So if the task is literally just create a patch that builds, you can send it through a compiler and see that it builds, and then you know deterministically if it was fixed or not. In other cases, you might have something that you want to judge that doesn't have easy to code in a rule-based way deterministic logic, and then you might make use of judge LLMs to assess the correctness or not of the model under test. And the judge LLMs themselves are not going to be perfect, so you need to make sure to have manual validation of those. Coverage and construct validity. You need to always be asking, does the benchmark actually measure the thing you care about? In many cases, it doesn't, and sometimes there's a trade-off between measuring exactly the thing you care about and having some sort of kind of like toy problem or challenge or multiple choice question that doesn't exactly represent what you want the LLM to do in the real world. All right, I'll get through the last ones. Okay. So the last two challenges, one is increasingly complex environments. I didn't touch on it, but for the auto patch bench, in order to run that benchmark, the LLM is communicating with a Docker container that hosts the code that has to rebuild it and then run the fuzzer. So there's a lot of complexity in building these things, more so the more complex agentic systems and more capable agents are becoming. Finally, benchmarks. This isn't specific to like cybersecurity, but keeping benchmarks from getting stale and making sure that they're not included in pre-training. Okay, so with that, I have the QR code here. If you're interested in AI security on my team and my colleagues here who are from the safety team, AI safety team, we're hiring, so please scan that. And I will take questions, but I realize we're also out of time, so please feel free to come up to me afterwards if we don't have time here. All right, thanks everyone.